make something exponential. How do I look at this example and say, yep, that's an exponential function? Where is the x? In the exponent, not x squared, right? That was quadratic. They're very similar, but the x is in the exponent. That's what makes it an exponential function. All right, I wrote down the exponential function is anything with x in the exponent, right? And I wrote down up here, any number raised to the 0 power always equals 1. Remember yesterday I put up on the board the pattern of all the powers of 2? And if it's the 0 power, it's always 1. Oh, I have another example that I always like to do because people can relate to folding a piece of paper in half, right? How many layers of paper do I have? How many times have I folded my paper? All right, now how many times did I fold the paper? I folded it once. How many layers do I have now? Okay. You guys ever seen the YouTube video of trying to fold a piece of paper 10 times in half?
I think I want to really do this.
Fold 0, layers 1. Fold 1, layers 2. What happens when I fold it a second time? How many layers of paper will I have? 4. And let me do it like one more time. I only folded it 3 times. How many layers of paper would I have? Okay, see how this is really 2 to the 0 power? 2 to the first is 2, 2 squared is 4, 2 cubed is 8. So that's another, just kind of like embedded in your mind. You can't have multiple layers if you don't start out with a layer of something to double, right? Because if you start out with 0 of something and you try to double it, you're still going to have 0, right? 0 doubled is still 0. If you have 0 money, you can't invest it in the bank, you can't double your money. You have to start out with something. So layers is also reinforcing anything to the 0 power is 1. What did you say the record is? Oh, so I only folded it 3 times. Oh, that would be 4 times. Yeah, see, 5 times. I think, was it on Mythbusters where they did it the size of the football field with a steamroller? Did they get to 7? Oh, okay. I should find that video. I thought it was Mythbusters. Okay, I'll have to look it up. Maybe we can watch it after lunch. Okay, so 2 to the x. How do I graph this function, 2 to the x? Well, let's set up a table of values just to help us get going here. Let's go from -2 to +3. And I'm going to start with the ones we know. We know anything to the 0 power is 1. So when I plug 0 into this function, 2 to the 0 power is 1, right? Sorry that my floor is shaking a lot today. That's the circulator on the roof, I think. Okay, what's 2 to the first power? That's basically that table that I made over there, right? 2 to the first is 2. 2 squared, if I plug in 2, would be 4. 2 cubed, if I plug in 3, would be 8. So those are all the powers of 2. Do you remember what happens with a negative exponent? The negative first power, the negative second power are the reciprocals of these, right? So if 2 to the first is 2, I take the reciprocal, that would be 1/2. And I would take the reciprocal, and that would be 1/4. So what would be -3? 1/8. All right, so let's plot these set of points, and that will give us our exponential curve. So at -2 for x, I'm just really close to the x-axis. And then I'm at 1/2. So I'm still really close to the x-axis, and then I'm finally at 1. Now I get to double. 1, 2, 2, 4, 3, 8. I'm just going to kind of lightly connect them. That's my curve. Your curve does not go under the x-axis. So make sure it like plateaus kind of flatly this direction. So it goes up real fast, but it plateaus to 0 I'm just going to mark this in a different color. These graphs have something called an asymptote. This might be your first function ever that has an asymptote. Asymptote, y equals 0. So your fraction is going to get smaller and smaller, right? 1/4, 1/8, 1/16, 1/32, 1/64, but it'll never be negative. So it's going to get really close to 0, but it'll never be negative. So you can write that you have an asymptote. That's this green line on the x-axis. My graph gets really small and it approaches y equals 0. That is the parent function for 2 to the x. We've never actually drawn the points for this function. So now you're going to be responsible for exponential graphs. Okay, you can make a table of values though. So table of values is there to help you. So now we're going to do a table of values for 3 to the x. We're going to set up our table the exact same way for all of our exponential functions. Some of the pattern is going to kind of be the same as what happened over here. Anything to the 0 power is 1. Over here, when I plug in 1, I just get 2. Over here, when I plug in 1, I'm going to get 3 because the base is 3. And then 3 squared should be 9, and 3 cubed should be 27. These are powers of 3. Over here, we had all the powers of 2. And then to go to the negative ones, remember those are just reciprocals of 1 and 2. So 3 and 9 would be 1/3 and 1/9. So when you go to graph these functions, you really only need, you don't have to write this, these 3 points. We know that 0 is comma 1, the base is the power, 3 to the first power is 3, and this is just the reciprocal. So it looks confusing right now, but if you keep hovering right around 0, you're just using the base and the reciprocal of the base every single time. So you don't have to like memorize too much. Memorize the shape. Okay, so I'm going to graph those points. 0, 1, 1 comma 3, and 3 squared is 9. And then 1/3 and 1/9 are just getting really close to that x-axis. I want you to compare for me the two graphs, 2 to the x and 3 to the x. This is my y equals 0 asymptote. So here they are side by side. How would you describe what they have that's different? What is different about those two graphs? They have the same asymptote. They have the same domain, right? I can go forever in both directions. Huh? Yeah, which one is steeper? 3 to the x. So the bigger the base is, the faster the population is growing, right? 4 to the x would be even steeper. 5 to the x would be even steeper. Okay, now we're going to take 2 and 3 to the x, and we're going to do their fractions, 1/2 and 1/3. Are we good on this one before I move it? Okay, these are the last two that I'm going to have you make a table of values for practice. So x and y, -2, -1, 0. This time I'm just going to go as far as 2. You'll see why in a minute. I'm going to start with the 0 power. Anything to the 0 power is always 1. My y-intercept is always going to be at 0, 1. When I take the first power of a fraction, right, 1/2 of the first power, I just get the fraction back again. And when I square the fraction, what's 1/2 times 1/2? 1/4. What happens when I take a fraction and I raise it to the negative first power? It's not happy where it is, right? It flips itself around and makes a reciprocal. So this is actually 2, and this is actually 4, right? It's the reciprocal of its partner. So if this is 1/2, the reciprocal is 2. If this is 1/4, the reciprocal is 4. It's just this function flipped over the y-axis. Because at -2, now I'm at 4. At -1, now I'm at 2. 1, 1/2, 1/4. See how it's coming down? This is called exponential decay. The other ones were called exponential growth. So this is population is decreasing over time, or your money is decreasing over time. The value of your car depreciates over time, right? As soon as you drive off the lot, it's not worth as much. It still has an asymptote right here at y equals 0. All right, and I want you to do the same thing for the 1/3 graph. I think you can do this table yourself and use the table up above and use the graph above to just flip it over the y-axis. I'm going to give you a minute to try number 4 yourself now that you've done 1, 2. All right, so let's fill that in. Anything to the 0 power is 1, then this will be 1/3, 1/9, and then the opposite direction of 3 and a 9. So it's growing on the left and it's getting smaller on the right. So at negative 2, I'm up to 9. Then I'm at 3, 1, and 1/3, 1/9. So this is a decaying at a faster rate, right? It's steeper than the 1/2, and this is y equals 0 still. So these are only 4 exponential graphs. I could give you other exponential graphs. I might have you graph 5 to the x. Let's think about what our key points would be. Anything to the 0 power is 1. When I plug in 1, what would I get? 1, 5 would be up here. When I plug in negative 1, I would be at 1/5. So you can pretty quickly graph those 3 points for any base. What if I did 9 to the x? Well, then you would start at 0, 1, 1, 9. It would be way up here. And then at negative 1, it would be 1/9. So you're just using the base and its reciprocal, 9 and 1/9, 5 and 1/5 to get your curve. Okay, so on this next page, it's having you actually draw some similarities and differences between 2 to the x and 1/2 to the x. So let's compare 2 to the x and 1/2 to the x from the front page. So just, you don't have to flip back, but one more time. This was the 2 to the x graph, and this was the 1/2 to the x graph. So we're going to try to come up with what is their domain. Actually, I might sketch it down here first, just so you can be looking at, okay, this graph looked like this, and this graph looked like this. What is their domain? So as I stretch my hands both directions, can I go forever? So they both have a domain of all real numbers. My hands can go forever up and down, so they keep going this way. Can I go forever up and down? Where do I get stopped up? Right at 0. I actually have to be bigger than 0. I'm not allowed to touch the asymptote. I approach it, but I don't actually pass through 0. My y-intercept every single time is what? 0, 1 every single time. When I plug in 0, anything to the 0 power is 1. This is called growth. So what do you think it's doing? As I read the graph from left to right, it's going up, right? So it's increasing from left to right. This one is decreasing. It's called decay. So, right, decay is decreasing. Growth is increasing. The horizontal asymptote we said was y equals 0 both times. These are continuous graphs. Next unit, we're going to study discrete sequences, where you can only have term 1, term 2, term 3, term 4. So it's going to look exponential, but we don't connect the dots next unit. Because when you guys get compound interest, maybe you only get monthly compound interest, or you only pay a car payment once per month. So you don't have a 2.5 months, interest, or 2.5 months rent. You have month 1, month 2, and month 3. So right now, this is continuous. It goes forever. Okay, and it says, does anything happen if we change the base to 4, 8, 100, 1/2, 1/5? It makes it steeper, right? So these get steeper for bigger base. That's the only thing that changes, is it gets steeper. All right, I want you to try making your own table and graphing. See if you can pick up on, what I did with the table and stuff. 1/4 to the x, and 10 to the x. Take a couple minutes and try those on your own. Set up a table for yourself. You're going to do both of these at the bottom. -2, -1, 0, 1, and 2 for both of these. -2, -1, 0, 1, and 2. And you're using 10 to the x and 1/4 to the x. See if you can do these by hand. You only have to do the base up to squaring it. I'm going to put it. So you'd want to be able to say, let's see, 1/4, 1/16, 4/16. So it's coming down -1, 0. I can't really fit 16, right? So I will just say it's coming really steeply down like that. And then this is the dotted line, y equals 0. So an asymptote is actually like a broken line, dot, 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 like that, to show you that you're kind of like, it's like a barrier. Like I can't go below that. And then 10 to the first, I can just do like 1, 10. So this is going like straight up. So the mistake that I see where people lose some points on the quiz is that I say to write the equation of the asymptote as part of your answer, and people will start to get lazy and they kind of like connect the dots and then they kind of go like that. Why would that be missing the point of this? What is wrong with this over here? I just went below 0, and that's something that is important that exponential functions, they plateau out. So if you do that, you're not showing that it's plateauing to the asymptote to get full credit. Oh, I want to do. Okay. And then the last page is, you can take a picture of this if you want, right before you go. These are the transformation rules for an exponential. Remember our up, down, left, right from quadratics? I just wanted to practice how to write them when you're looking at an exponential. And we've already looked at these this year. It shouldn't be anything new. But if you're going up, I like writing y equals better than f of x equals, but y equals 2 to x. What's your favorite number? Give me a number. So plus 5 would shift this graph up 5 units. So this is like outside of the function. So if I wanted to go down 5 units, I would do a big -5 outside of the function. Does that feel familiar? It's quadratic, right? A quadratic would have been x squared plus 5, x squared minus 5 from the unit 3 test. Okay, now to go to the right, you write it up with the x up here. So x minus 5 is little. It's up in that exponent. It's kind of like, let me think, x minus 5 squared was in parentheses for a quadratic. You can kind of think of like this is a parenthesis because it's in the exponent. It's kind of like a parenthesis, but usually we don't write a parenthesis up there. And if we want to go to the left, we write the little superscript 2 to the x plus 5. If you write on your test the equation is 2x, that is going to be wrong. Do you see the subtle difference in these two? This is a linear function, right? X is the same size as the 2. This x is a little superscript in the exponent. So I will take off points if you write 2 times x. It's 2 to the x power. If you reflect over, it would be y equals -2 to the x. That flips it upside down. And if you want to flip it over the y-axis, this is the same as y equals 1/2 to the x power, right? We just saw this on the front page. If it's a negative exponent, doesn't it flip it upside down to make it a positive exponent? So it should make sense that if you're flipping from here to here, right, from here to here, that's a flip over the y-axis. It's the same as writing it as the fraction 1/2. This is completely flipping it upside down. So you're taking 2 to the x that's up here, and you're flipping it upside down, 2 to the negative in front. Actually, it might be good to put an example on your notes of what that would look like. So maybe just draw a little arrow down to where you might have room, and you could write -2 to the x would look like this. right? Because it's starting like this and it's flipping upside down. 2 to the negative x would look like this, right? Because it's starting from here and it's flipping over the y-axis versus the x-axis. Well, the reflections are just being shown down here. So this is if you have a negative in front, it flips it over the x-axis. And if you have a negative like this, it's going to flip it over the y-axis. That's kind of what I meant. And then the vertical stretch, let's see, would be like y equals 3 times 2 to the x, or y equals 1/2 times 2 to the x, right? The bigger number stretches it, the smaller number shrinks it. A changes the y-intercept, so you're going to see this next part of the unit. B is the steepness. These I wouldn't worry about for the quiz this week. Yeah, I just wanted people to be able to copy this if they needed to write that one down. Because it's gonna ding for lunch, and then I'll show you